We know that in metal atoms, when metal atoms are bonded to each other, the electrons are able to flow from one atom to another. And so when the electrons all tend to flow in a specific direction, that's what we call electric current. Electrical energy can be transferred into or out of a system through the movement of charged particles. So when the electrons move through the wire, we actually get electrical energy um, we get electrical energy which is transferred through the system. And it happens sort of like this animation on the bottom left. It's not, again, remember, models all have limitations. This model is not an exact representation of what happens, but generally speaking, the electrons are caused to flow in one direction, and that is called the electric current. When, in this case, in the animation, we see the electrons are flowing from left to right. The current then, uh, and this is counterintuitive. This is not what we would expect. But when the electrons flow left to right, we say that the current is actually flowing from right to left. So the direction of flow of electrons is actually opposite the direction of the current. And this is because a couple of hundred years ago, or more than a couple of hundred years ago, when Benjamin Franklin was studying electricity, he had, nobody in the world had any idea what electrons were. It would be over 100 years before electrons were discovered. But he was studying electricity, and he was able to determine that electricity does indeed flow in one direction. And he just designated one direction as positive and the other direction as negative. And later on, we found that the direction that the electrons are flowing is in the is in the negative direction. So the current is opposite the direction of flow of electrons. If Benjamin Franklin had designated positive and negative in the opposite directions, electricity would make a bit more sense now. But we've stuck with the conventions that we used for hundreds of years. So if you have two wires carrying electrical energy, and then the first one is carrying twice as much energy of the second as the second, think about if they're both copper wires, say, what explains this difference in energy? Well, there could be a few different things, right? It could be that, well, let's look at this next image. In this image, we see how electrons um, tend to move through a wire. They don't move in a straight line like the previous image. They tend to move rather erratically, and when the direction is in a general, like if this electron was generally, we can see it's generally moving to the right, well, that would generate some electric current. And we can see in this image, we can see if the velocity of that electron is from left to right, because velocity is a vector, it has direction. If the velocity of that vector is from left to right, the direction of the current is actually from right to left. Now, the amount of current that's flowing can be determined by, if you think about it, by different things. It can be that the path of this electron could be more direct, less zigzaggy, right? It could be that there are more electrons in the wire that are moving generally left to right. So they can have more direct flows. Um, they could move faster. Maybe they move faster. So any of these things would result in more energy. Well, we have a way of measuring the electric current. We have a unit for electric current, which is called the ampere. And you're going to want to write that in your notes, Ampere. Or we usually just shorten that, even though it's a pretty short word to begin with. We usually just call it amps, A-M-P. An ampere, or an amp, is equal to 1 coulomb per second. So we know that electric charge is measured in coulombs, and if one just like velocity would be measured in meters per second, which is how many meters an object moves through 1 second. current is measured in coulombs per second. So it's how many coulombs of charge pass a point every second. A coulomb, remember, is a unit of charge, and it would actually be equal to a pretty huge number. One coulomb, if we're talking about the charge of an individual object, remember we use microcoulombs. So one coulomb is a pretty sizable amount of charge. So when we're looking at two different things. Drift velocity. Drift velocity is the idea that electrons are always moving, or it's based on the idea that electrons are always moving through a conductor. Even though electrons are always moving through a conductor, they don't always move in the same direction, but they do kind of drift through the conductor from atom to atom. They move in this erratic path, but if you put the conductor in an electric field, so in the presence of an electric field, the random motion, it'll still be pretty random, but it will generally move from one side of the conductor to the other. So that will be your drift velocity. The drift velocity is fast the um, how fast the electrons themselves move through the conductor. And remember, the current is opposite the direction. The direction of the current is opposite the direction of the drift velocity. The drift velocity is determined by the strength of the electric field in the wire. The stronger the field, the more it accelerates the free electrons. So as the drift velocity increases, the current, or the number of electrons passing through a cross section of the wire, also increases. When the electrical energy is transferred, or when the electrons flow through the wire, then the energy transfer is carried by that electric current. And again, the direction of that electric current is opposite the flow of electrons. If the electrons are flowing left to right, if their drift velocity is left to right, then the current would be right to left. When electrons move through a solid like a copper wire, they don't move in a straight line. They bounce around and generally move left to right or right to left. And when I say the current moves right to left, I mean even though something is physically moving left to right, when we describe the current flow, we're describing the flow of positive charges. Okay, so the flow of positive charges is the direction of the current, even though it's actually a negatively charged object that is physically moving through the wire. When a negatively charged object physically moves through the wire, you get a flow of positive charge in the opposite direction. In a circuit, the direction of electron drift and the direction of current are opposite. So in this case, we see a battery. The battery has a conductor attached to the positive and negative ends, the positive terminal and negative terminal of the battery. We would describe the flow of the current as going from the positive end to the negative end. Even though the electrons are gathered at the negative end of the battery, so the electrons actually flow from the negative end of the battery to the positive end. This is what's called an electric circuit. An electric circuit is a loop of the conductor. It's a loop of conductive material through which a charge can move continuously. So the electrons can drift in one direction through the conductor. If you were to break this wire, then the electrons could no longer flow through it, and we would no longer have an electric circuit. In fact, that's all that a switch is. A switch is something that breaks that circuit, and that prevents it disconnects the positive end. In the case of a battery, it disconnects the positive end from the negative end, because there's a break in the circuit and electricity can no longer flow through there. A battery provides an electric potential difference that generates the flow of charge through the circuit. And this is where the potential energy comes from. The potential difference in an object in Earth's gravitational field would be if you pick it up off the floor and hold it up in the air, then that's a gravitational potential difference. The potential energy is different when it's held up in the air than when it's sitting on the ground. In an electric circuit, you have electric potential difference, and that's what so you have a greater amount of electric potential in one place and a lesser amount of electric potential in the other place, and that's what causes the electrons to flow and the current to flow. This is called voltage, and of course that's a vocabulary word you're going to write in your notes. The electric potential difference, another word for electric potential difference, is voltage. Voltage is the amount of work, and here's your definition. Voltage is the amount of work to move a unit electric charge between 2 points. And the unit for voltage is volts. So when you hear about the voltage of an electrical system, then that's just referring to how much work it takes to move an electric charge from one point to another.